Today we're diving into a new idea, fractal generative models. Instead of a single model struggling to create an entire image, this approach breaks the problem down recursively. Each small generative model builds on itself, like an army of tiny artists sketching different levels of detail. And the result? Ultra-detailed images generated pixel by pixel, all while keeping computation under control. Buckle up as we are diving into it. Let's go!
Let's talk about fractals and generative models. Ever wonder what makes fractals special? They're self-repeating structures, like snowflakes or coastlines, built by applying the same transformation again and again at different scales. This paper introduces a new kind of generative model that behaves like a fractal. The core concept here is modularization. In deep learning, we usually build modules, like layers in a neural network, or steps in a generative process. But what if the entire generative model itself was a module? What if it could call itself over and over at different scales? That's what the fractal generative model does. Instead of one huge generator, this method creates final outputs by invoking smaller generative models inside itself. Picture a group of tiny artists, each handling part of the image, but all following the same overall rules. This self-similarity is what makes it fractal-like. Look at the figure here. On the left, you'll see a single generator that splits into multiple sub-generators, which then split further. On the right, you'll see the result of this recursive process, a fractal structure where each piece resembles the entire whole. This approach could be especially helpful for pixel-by-pixel image generation, where we need to capture fine details and global coherence at the same time. This introduction sets up everything we'll explore: how fractal generative models work, and why they might be so effective in AI-generated content. Fractals aren't just mathematical curiosities, they're found everywhere in nature. Think of branching trees, the structure of lungs, and the patterns in clouds. Even our brains form complex networks out of smaller repeating units. That's exactly the principle behind this fractal generative model. Instead of seeing an image as one big grid of pixels, the model views it as a set of smaller sub-images, each generated in the same recursive manner. It's like how a tree grows by repeating a simple branching pattern at multiple scales. This concept is tested on a notoriously hard task: generating images pixel by pixel. Many models struggle with this because images don't have an obvious one-dimensional structure. But by letting the image unfold as self-similar components, the fractal model finds a natural way to handle high-resolution details. Look at figure 2 here. The model starts with a rough structure and refines it in steps. Instead of generating the entire image all at once, it predicts patches of pixels in a recursive fashion, zooming in to add finer details each time. By the final stage, it's predicting RGB values pixel by pixel. Although the focus here is on images, the same fractal idea could be applied to anything else with an underlying repetitive structure, like molecular configurations or protein folding. If your data is built from smaller repeating parts, a fractal approach might be the perfect fit. Hierarchies are a big deal in computer vision. Early feature extraction methods like SIFT and Laplacian pyramids rely on scale space analysis, which captures patterns at multiple levels. Modern architectures, such as the Swin transformer, also use a hierarchical approach by working on smaller local image patches first, then expanding to the whole image. Generative models benefit from hierarchies too. Some models compress an image into a lower dimensional latent space before refining details. Others, like Megabyte, combine local and global components to balance speed with accuracy. And diffusion models build up images progressively, starting with coarse details and getting finer over time. Modularity ties everything together. Neural networks already use modular building blocks, like convolutional layers or attention blocks, to decompose large tasks into smaller ones. Fractal generative models push modularity even further. They make entire generative models act as recursive building blocks. This goes beyond approaches like FractalNet, which simply repeated deep network structures. By allowing the model itself to invoke smaller generative units, the result is something that can scale exponentially, with only a modest number of fractal levels. All in all, it's a very different way to think about generation. Instead of a classic top-down or bottom-up pipeline, the fractal model uses self-similarity, recursion, and hierarchical design to tackle high-dimensional data more efficiently. How does all this actually work? The paper uses autoregressive models as the foundational building blocks of the fractal approach. Instead of one giant model trying to generate every single pixel at once, the process is split into smaller chunks. Here's the workflow. The fractal model begins by grouping the data, say, image pixels, into chunks. The first level of the fractal learns to generate these groups. Then, Each group gets broken down even further at the next level, which refines the details. This keeps going until the entire image, or dataset, is fully generated. This divide and conquer method offers two main benefits. First, it's computationally more efficient, because each step is focused on a smaller subtask. Second, it's naturally hierarchical, refining details level by level, much like how fractals form in the real world. In practice, the paper tackles pixel-by-pixel image generation. Traditional methods can find this difficult because they try to capture all the global structure at once. A fractal approach, however, can build an image by applying the same local rules repeatedly, just like nature does in tree branches or shell spirals. Even beyond images, the fractal model could be applied to other structured data, such as molecular or neural network architectures. The main takeaway? If your data can be broken down into repeating patterns, a fractal approach might let you capture it more elegantly. So how does the fractal model actually generate an image, step by step? The key is that the image isn't treated as a monolith. It's generated recursively, moving from coarse to fine detail. Look at figure 3 here. Each level of the fractal model uses an autoregressive approach with multiple transformer blocks, taking the previous level's output plus local image patches as input. Then it predicts the next stage of the image. This cascades down to the finest level, where a smaller transformer predicts actual RGB values at each pixel. Check out Table 1 next. It shows how the model scales across different levels. At the coarsest level, we have a larger hidden dimension and more transformer layers. But as the model zeroes in on smaller patches, those dimensions and layer counts decrease. This keeps the overall computation efficient. Generating a 256 × 256 image only costs about twice as much compute as generating a 64 × 64 image. Much better than the quadratic blowup we'd get with many typical models. Compared to scale-space autoregressive models, which try to handle all pixel dependencies in one shot, the fractal method uses attention only within small patches before moving on. This approach is about 4,000 times more efficient in high-resolution scenarios, making true pixel-level generation more viable than before. Efficiency is the name of the game here. Rather than brute-forcing millions of pixel relationships, the fractal model incrementally refines details in a self-similar way, much like nature's own fractal processes. How does this fractal approach measure up against the usual methods? Traditional pixel-by-pixel models borrow ideas from language modeling, viewing the image as one very long sequence. But images aren't just long sequences. They have intricate structures made of smaller parts, whether those parts are patches of pixels or subblocks of objects. The fractal model addresses this by treating an image as hierarchical subcomponents. Each subcomponent is modeled recursively, so local structures can be learned independently before scaling up. Check out Table 2. You'll see that adding more fractal levels improves likelihood estimation while reducing compute time. Full-length autoregressive models often demand enormous flops, but fractal models achieve comparable results with much smaller costs. And if you turn to Table 3, you'll find that these fractal models match or exceed the performance of top generative methods like diffusion models and pixel RNN on likelihood metrics. The difference? Fractal models are more efficient. They keep computational demands in check by focusing attention on smaller patches first. Training is done end-to-end. Each autoregressive unit refines what the previous level produced, and the model generates images in a depth-first order, going from larger structures down to the pixel level. All in all, fractal generative models appear to be competitive in quality and significantly cheaper to run, an interesting combination for high-resolution image generation tasks. Curious about the actual quality of the generated images? Figure 4 shows some examples of pixel-by-pixel image generation. You'll see detailed images of animals, household items, and more, all created from scratch at high resolution. Why does this work so well? The key lies in how many fractal levels are used. The paper compares models with different numbers of levels. Adding more levels makes the model more efficient and better at capturing structure. A model that tries to jump straight to 64 × 64 pixel generation can be expensive, while a 2-level fractal model that splits pixel sequences and RGB values still uses a ton of compute. A 3-level fractal approach, on the other hand, spreads out the workload and reduces computational costs. The paper also reports some standard metrics: Fréchet inception distance, or FID, inception score, and precision. The fractal model achieves an AFID of 6.15 and an inception score of 348.9 when generating 256 × 256 images. It takes about 1.29 seconds per image on a single NVIDIA H100 GPU. The images themselves are high quality with strong precision, though they show slightly weaker recall. So while the generated images look sharp, the model may not capture every variation in the datasets. Still, it demonstrates that fractal-level recursion can produce realistic, detailed images without breaking the bank on compute. Finally, how does this fractal model compare with leading methods like Gaussians, diffusion models, and other autoregressive approaches? Check out Table 4 to see how they stack up at 256 × 256 resolution. The main metric is FID-lower is generally better. FractalMar might not beat the top GANs like StyleGAN, but it outperforms many alternatives, especially among autoregressive models. It also has high inception scores and precision, indicating that the generated images are quite realistic. Recall is slightly lower, which implies a narrower coverage of the full data variety, but the trade-off might be worth it depending on your application. Look at Figure 5 for some image editing examples. The model handles inpainting, filling in missing parts, outpainting, extending images, uncropping, reconstructing large missing regions, and class-conditional editing, changing an object's identity with ease. Because it operates directly at the pixel level, its predictions are transparent and interpretable. That's a contrast to models like diffusion, which work in a latent space. This pixel-level approach opens doors for more controllable or interactive scenarios, such as editing visual content or exploring new designs. So in short, FractalMar is on par with top generative models in many respects. It gives you a solid mix of quality, efficiency, and interpretability, especially if you need pixel-level control. Thanks for joining us today. Happy learning and stretching together.